Last time we considered a linear oscillator. This time we're going to consider a nonlinear oscillator. So this is a version of the Rayleigh oscillator. And in our case, we're going to look at an equation d2y dt squared plus epsilon 1/3 dy dt cubed minus 9 dy dt plus 4y equals 0. And we're going to try and use a two-scale method to get us a general solution to this. So note that when dy dt is small, this term dominates and is negative. So we actually have negative damping when dy dt is small. It's only when the dy dt is large that this term takes over and we get standard damping. So as is usual for two-scale, we're going to say that y of t we can rewrite as y of t tau, where tau is epsilon t. So we can use that to rewrite the derivatives. So dy dt is dy dt plus epsilon dy d tau, and as before d2y dt squared is d2y dt squared plus 2 epsilon d2y dt d tau plus epsilon squared d2y d tau squared. So if we take our differential equation and substitute that in, we get d2y dt squared plus 2 epsilon d2y dt d tau plus epsilon squared d2y d tau squared plus epsilon 1/3 dy dt plus epsilon dy d tau cubed minus 9 dy dt plus epsilon dy d tau, close that bracket, plus 4y, all equals 0. So my next step is I'm going to substitute in a perturbation expansion. So I'm going to take this equation, so I'm going to sub in y is y0 plus epsilon y1. I'm only going to keep terms epsilon to 0, epsilon to 1. So epsilon squared, epsilon cubed, I'm just not going to bother to write down. So that gets me d2y0 dt squared plus epsilon d2y1 dt squared plus 2 epsilon d2y0 dt d tau. Now my damping terms already had an epsilon in them, so I'm only going to keep the y0 terms from them. So that gets me epsilon on 3 dy0 dt cubed minus 9 epsilon dy dy0 dt plus 4 y0 plus 4 epsilon y1, and all that equals 0.